Hello everyone, my name is Moussa. I am a PhD student in the Department of Nuclear Engineering at the University of New Mexico. My advisor is Dr. Anil Prinja, and the title of today's presentation is Direct and Moment Reconstructed Fast Neutron Multiplicity Distribution Computations. So, from previous work that's been published in the nuclear safeguards measurement space, we've seen that multiplicity distributions provide unique signatures for material property identification. Non-destructive assay techniques, such as coincidence counting or multiplicity counting, are widely used in this space to infer details about special nuclear material samples. These techniques typically rely on measuring the multiplicity distribution, then extracting lower order moments. So you can see how being able to accurately compute multiplicity distribution is complementary to multiplicity counting measurements. A simple example is the plot you see here on the right, where you have the spontaneous fission multiplicity distribution plotted in red, a Poisson normalized to the same mean as the solid blue line, and the distribution produced by a multiplying sample is what you see in green. The deviation of the tail away from the Poisson is a clear indicator that there's multiplication going on. Traditionally, point kinetic models are used to relate the singlets, doublets, and triplets to sample mass and multiplication. In this work, we present an efficient method for reconstructing multiplicity distributions from readily computed low-order moments and low-order count number probabilities. Now, the quantities we are interested in are P of n, which is the probability that n counts are registered in a finite time interval d, given that one neutron was introduced into the system at an earlier time s, and theta of n, the probability that n counts are registered given that an intrinsic random source is turned on at an earlier time. So, by conducting a probability balance of all independent mutually exclusive events, we were able to derive backward master equations for both quantities. You probably saw this in some of our previous presentations where applying the generating function transformation and taking the kth derivative evaluated at z equals 0, we get equations for p and theta that you see here. In these equations, I and j are the derivatives of the branching terms evaluated at z equals 0. After writing out the first few terms, we recognized the pattern, and from that we were able to derive a recursive relationship, which we list down here for both I and j. An important thing to point out here is that the equation for P0 is standalone but nonlinear. The rest are linear, but they're fully coupled, which creates a numerical challenge as the number of counts increases. So the equations have to be solved sequentially by backward integration in time. So I was able to write a lambda function in C++ that evaluates I and j at every step and solve these equations to an arbitrary order. However, it gets to a point where the computational cost no longer makes it feasible. We believe we can advance on this, and we're currently investigating some methods that have the potential to speed up this calculation. Now, before we get into the results, I want to take the time to go over the sample problem we're investigating and where the data we're using came from. So the source is a plutonium sphere made of 80% Pu-239 and 20% Pu-240. You've probably seen this source used in many studies before, but a challenge we faced was where would you get point kinetic parameters for this problem? In particular, what is the leakage rate in a point model? So what we did was we ran a standard adjoint weighted 1D spherical geometry transport calculation, and from that we got the values for all the reaction rates in the equations we're solving. Another thing I'd like to point out is that we benchmarked all the results generated for this presentation and this study so far in general against a stochastic simulation algorithm that we've talked about in previous papers and presentations, where for those of you who are unfamiliar, it's a system state updating Monte Carlo method. It basically moves the state of the system at once as opposed to simulating individual chains. We're working on getting this published, so for those of you who are interested and want to read more, we'll have a paper on this soon. Now, what you see on the bottom right here is a plot from work that's been previously published that we were able to reproduce using the SSA method, and to the far right is the multiplicity data used for the simulation. Moving on to the results of the direct computation of the count distribution, what you see on the left is the count distribution produced by a 335 gram sample of the plutonium source simulated over a 17 microsecond time gate. It shows excellent agreement with the SSA simulation, where the standard deviation in the SSA is approximately 1% at the peak, and it goes up to about 5% at the tail. On the right is the same type of plot, but for a 2680 gram source simulated over a 2 microsecond time gate. We also see excellent agreement with SSA here, where the standard deviation is again approximately 1% at the peak, and it goes up to about 5% at the tail. Now, the computation time in comparison with SSA was, again, the challenge with the direct computation of the multiplicity distribution. So the computation time for the 335 gram case is 36 seconds for SSA and about 2.5 minutes for the exact computation. The 2680 case, SSA took 53 seconds and the exact computation took about 97 seconds. So this pushed us towards looking for other methods to reproduce the count distribution more efficiently. And that's what I'd like to talk about now. So we've seen that the backward master equation can be solved for the individual count number probabilities. But for large count numbers, this becomes tedious. However, we found that the numerical solution is quite efficient for the moments of the multiplicity distribution. So we had to ask the question, can the probability distribution be reconstructed from a finite, preferably small, number of moments? And to answer that question, we derived equations for the factorial moments. This was done in a very similar way to how the count equations were obtained, where we evaluated the derivative of the generating function equations at z equals to 1 instead of z equals to 0. And those are the equations that you see here. One thing I'd like to point out about the source terms Q and QS, these terms introduce a coupling factor, as we previously saw, where each moment will depend on the previous moments. So they had to be solved numerically, similarly to what was done for the count equations. And now that we have the moments, two approaches were used to reconstruct the count distribution: orthogonal polynomial method and the maximum entropy method. The first method, the orthogonal polynomial method, is a variation of the gamma distribution. The gamma distribution itself, which is stated here, was taken to preserve the first and second moment. An important thing to note here is this eta parameter, which is inversely proportional to the variance to mean ratio. I point this out because the value of this parameter will dictate the shape of the distribution. So using this method, we're able to derive distributions that preserve higher order moments as well, not just the first two. This is done through a truncated expansion in generalized Laguerre polynomials, which leads us to the distribution you see boxed here. A couple things I'd like to point out here. One, the expansion starts at k equals 3. Since the gamma distribution preserves the first two moments, and you can see it depends on these expansion coefficients, these a sub k. Those are obtained by enforcing the preservation of the true moments up to an arbitrary order. So again, we have a 335 gram sample, but this time it's sampled over a 84 microsecond time gate. The plot shows the SSA compared against the gamma distribution alone, the gamma plus the third and fourth moments, and the gamma plus all moments up to the sixth moment. The standard deviation of the SSA simulation was about 1% at the peak, and it goes up to 15 at the tail. And you can see that adding up to 6 moment does a good job at capturing the distribution, but even 4 does good as well. And the table at the bottom here shows how the root mean square error decreases as more moments are preserved. A few things worth noting here, though, are the reconstruction distribution is undefined at n equals 0. So you see on the plot, the reconstructed distribution starts at n equal to 1. But that's not a problem because we can very efficiently compute P0 since it's a standalone equation. Another thing is the distribution jumps drastically within a few counts. This could be part of the reason why more moments are needed to accurately reproduce this distribution. The same thing is done on the right for a 2680 gram sample, but this was simulated over a 19 microsecond time gate. Here you see less moments are required since the number of counts is larger and there are no drastic changes anywhere. The standard deviation in the SSA simulation here was about 2% at the peak, and it went up to 15 at the tail. And again, you see the root mean square error going down as you add more moments. As far as computation time goes, this is where we see big improvements. For the 335 case, SSA took about 149 seconds, so that's about 2.5 minutes. The Gamma-Laguerre expansion, including the time to compute the first 6 moments, took 0.02 seconds. That is less than 1% of the time it took for the SSA. For the 2680 gram case, SSA took 456 seconds and the reconstruction took only 0.002 seconds. So you can see how powerful these methods can be. Now, in the previous slides, I pointed out that the eta parameter dictates the shape of this distribution. And you see that becomes an issue when the time gate is small enough for the variance to mean to be larger than the mean number of counts. This leads to eta falling below 1. At that point, the distribution is monotonically decreasing, and the reconstruction distribution fails to capture these low order counts. You can see that in the plot here on the left where 2680 gram sample is simulated over a 6 microsecond time gate. On the other hand, when the number of counts is very large, so either a very big time gate or a strongly multiplying system, the gamma distribution alone does a good job at reproducing the distribution. The plot on the right shows a 9047 gram sample plotted over multiple time gates increasing in size, and even though the smallest time gate shows a difference between the gamma and the third moment on the order of 10 to the minus 5, the largest time gate practically shows no difference. The second method is the maximum entropy method. The idea behind this method is that the neutron count probability distribution that maximizes the information or Shannon entropy is the one that is statistically most likely to occur. So the entropy is defined as negative p log p, and what we want to do is maximize this entropy. The way we do that is by solving for these Lagrange multipliers, these lambda k's that you see here, that preserve specific constraints that we're imposing on the distribution. In this case, those constraints are the exact moments of the distribution and a number of exact low order count probabilities. Our initial analysis showed that it is more efficient to use normalized central moments as opposed to factorial moments, so that's what we chose here. We started by looking at the moments alone, but we have the same problem we faced with the orthogonal polynomial expansion. The reconstructed distribution failed to capture the low order counts. But as we've seen, we can easily compute the low order counts, so we went back and added the exact discrete probabilities as constraints. That led to the functional h that you see here. With some algebra and maximizing that functional, we're able to approximate the count distribution by the function boxed here. So when n is less than n star, the exact distribution are used. When n is greater than n star, the distribution is approximated by this exponential. And here you can see for a 335 gram sample simulated over 84 microsecond time gate, This is basically the same plot we showed previously for the orthogonal polynomial expansion. So the standard deviation again is 1% here at the peak and about 15% at the tail. The plot shows that adding the discrete points as constraint increases the accuracy of the reconstruction. But the moments alone still do a very good job at capturing the distribution as well. You can see this from the table at the bottom by looking at the root mean square error. This is a scenario that we already knew that the moment-only reconstruction method worked well for. But how about scenarios where they don't? And that's what we show here for the 2680 gram sample simulated over a 6 microsecond time gate. You see the moment only maximum entropy reconstruction fails to capture the low order counts. And by including those points as constraints with as little as 6 points, so that's 0 through 5, we already see a drastic increase in accuracy. But by adding 11 points, 0 through 10, the distributions are almost identical. You can see how the decreasing trend in the root mean square error below the plot here. And again, this is the same plot used for the orthogonal polynomial expansion, so the standard deviation is about 1.5% here at the peak, and it goes up to 7% at the end of the tail. Comparing the computation time between the SSA and the maximum entropy method, for the 335 gram case, SSA took 149 seconds. The maximum entropy, on the other hand, took 0.01 seconds for the moments only and 1.21 seconds for moments and the first 6 points. So you can already see that's a big difference there. For the 2680 gram case, on the other hand, SSA took 151 seconds, while the maximum entropy reconstruction only took 0.02 seconds for the moments only, 0.11 seconds for the moments and the first 6 points, and 1.87 seconds for the moments plus the first 11 points. So in conclusion, we've demonstrated a methodology for direct computation and moment-based reconstruction of neutron multiplicity distributions. For low count number, the multiplicity distribution was computed directly. For intermediate counts, we showed that the maximum entropy constrained by both moments and low-order discrete count probabilities was very efficient. And for large count number, the generalized Laguerre polynomial representation based only on the statistical moments was used. From here, we've started moving towards incorporating neutron phase space dependence and using deterministic neutron transport methods to solve the appropriate backward master equations and associated moment equations. Another thing we're working on as well is extending the multiplicity reconstruction methods to unlumped geometry and benchmarking against MCMP simulations. To that end, I've started an internship with Los Alamos National Laboratories under the mentorship of Jessen Hutchinson, where I'll be working on uncertainty quantification, and I hope to gain more experience developing MCMP benchmark simulations. With that, I would like to thank everyone involved in making this work possible. First and foremost, my advisor, Dr. Anil Prinja. I'd like to also thank Jessen Hutchinson and Aaron Davis from Los Alamos National Laboratories. And last but not least, the Consortium for Monitoring Technology and Verification, the National Nuclear Security Administration, and the Department of Energy for the continued support of these research activities. Thank you all for your attention, and I'd be happy to answer any questions at this point.